if you want to. While Gareth is getting his laptop going, Gareth Robbins is the Director of Analytics at EROAD and oversees EROAD's global transportation research. His work currently focuses on the use of GPS data to augment traditional methodologies to improve the safety and efficiency of the road network. Gareth has lived the analytics life for 15 years and has worked in New Zealand, Australia, and the United States, and is an active participant in a number of TRB committees.
Thank you. All right, good afternoon, everybody. Thanks for the introduction. I'm Gareth Robbins from Auckland in New Zealand. I'm going to talk to you today about a model that we've produced in New Zealand around predicting crashes using some of the data that our devices create. But before I go into that, I really want to talk about the why we actually did this in the first place. So hands up if you've been to New Zealand. That's good, there's a couple of you. So you know it's a beautiful place, and this is kind of the picturesque scene that everybody sees. Wonderful driving, we've got lots of hobbits in the hills. We've got unfortunately the second best rugby team now in the world after a couple of weeks ago, which I'm still a bit sore about. But we have a deep, dark secret. We actually have a really bad road safety record, despite all this wonderful greenery and tourism that brings people here. Last year, 377 people died on our roads, which for a very small country is a huge number of people. And that equates, when you look at the social costs of that, to around $4.8 billion, with the loss of life, disability, vehicle costs, legal costs, medical costs, and what have you. And as I say, we're actually ranked fairly low in the OECD, we're third from the bottom, and our situation's not getting any better. On the right, you see the rate of deaths and serious injuries is increasing at a much faster pace than our GDP and our VKT, or vehicle kilometres travelled. And we need to figure out why. So Ministry of Transport in 2017 asked Deloitte to do a study in this, and Deloitte found that about a third of this increase was due to just more stuff happening on the roads. More vehicles on the roads, more kilometres travelled. About a third was increased motorcycle registrations as people escape congestion and they want to improve their travel time to work. And a third of it is just unknown. They didn't know. There's a lot of theories that could be attributed to that. But that last third is kind of an opportunity to start thinking innovatively around road safety in the country. So in New Zealand we have the safe systems approach. And it really says that we know that people are going to crash. You know, people make mistakes all the time, but let's make those crashes survivable. Let's not make death the only outcome from those crashes. So it looks at the roads, are they fit for use? The roadsides, are the facilities in the right place? Are the speeds correct for the roads? Looks at the vehicles themselves, are they fit for driving? And then it looks at the drivers and the driver behaviour. And a lot of interventions are put in place to try and reduce these deaths. So here's some of them up here. And they're really successful. They have actually lowered the deaths and serious injury rate. But you'll notice on the right hand side, the time to realise this improvement is in the years in some cases. We're actually waiting for somebody to die before we know whether our intervention has actually worked, which is kind of a sobering thought. And this kind of sums it up, that we're kind of waiting for a crash to happen. You know, a crash happens and then there's an outcome, and we have all those social costs of $4.8 billion and deaths and serious injuries. And then we do an investigation and we try and figure out why, and we try and put into place an intervention and we lower some risk. But then a whole bunch of stuff happens between that risk and another crash happening. We don't know whether there's near misses in the country or not. We only know the bad stuff, and the ambulance is already at the bottom of the cliff, right? I know this is a bit depressing, I understand, it gets better. So where EROAD fits in is, in New Zealand we have a road user charge system. So heavy vehicles pay to drive on the roads. They pre-purchase mileage and then they use up that mileage as they go. When it was introduced, it was a paper-based system. You see on the left-hand side, it was a ticket you put on your windscreen, and it was displayed with the odometer reading and how much distance there are to go. EROAD came in with an electronic solution, and we made these devices that fit in the cab and then track the kilometres driven and work out whether the vehicle's on road or off road. And there's two great things that come out of that. One is obviously the products and services for our customers to enable fleet management, driver behaviour and what have you. And then the other one is the data that comes off these devices. So worldwide we have about 100,000 connected devices. In New Zealand we have about 75,000, which is a huge proportion of New Zealand's road network. And back to our why, this is what we believe in. So yes, we have a telematics business, but we actually want to make the roads better for every New Zealander, not just for our customers. Because if we can do that, then everybody sort of wins, right? So where I'm involved is taking that data and using it in an aggregated, anonymized way to protect the privacy of those customers, and then see how can we work with road controlling authorities to improve those roads. And we do a lot of cool stuff. So we do things around ports, so we do resiliency studies. There's a big earthquake in Kaikoura, and we figured out where the vehicles were going. We do a bunch of stuff in the United States as well. Work with Oregon State University. So there's a lot of cool stuff that we kind of do. But what I want to talk about today is harsh braking specifically. So harsh braking is just one subset of our data. So every time a vehicle slams on the brakes and comes to an abrupt stop, we create an event. And we know where that is. And when you put that all on the map, you can start to do some really cool things. We have about one harsh braking event every 4 seconds in the country. So there's about 8 million events every year. This picture here is Auckland, and the big dotted line, that's the main motorway in Auckland. You don't get much of a choice with travel. And to put it into context, this is kind of all of New Zealand's driver behaviour. That little dot way down here, that's kind of how big the crash data is that everybody works on in the country. So harsh braking compared to, for every crash data, we get about 900 harsh braking events, for example, to map out the scale. For every crash data point, we actually have about 1.4 million telematics events. So because harsh braking is just a subset of that much, much bigger data set. But I'll do something I've never done before. I'm actually going to show you the data, so I'm really hoping this is going to work. So I'll take you through a little bit of a story map here. So this is New Zealand, if you didn't know that already. These dots represent all the crashes from 2015 to 2018. So the size of the crash is the number of people that have been hurt or killed. There was a huge crash down here where a bus unfortunately turned on a corner. 27 people were injured seriously and 4 people died. Up in Auckland, you have a lot of the crashes. So there's actually quite a few down by my house, unfortunately, so I've got to be careful. But you know, you can see the scale of the crashes, and that's quite extraordinary. But that's 4 years worth. If we look at the harsh braking data from EROAD, this is just 1 month's worth. So it's I couldn't put 4 years worth on an interactive map, unfortunately, because the computer would just die. But you get this really, really rich data set at every intersection pretty much around the country. You get a lot of these harsh brakings happening here. You can see coming off the motorway, going from the motorway into the local roads. You get quite a few people stopping at the lights. And then you get a lot down in the rural areas as people negotiate New Zealand's really, really rough terrain. To give you an idea of sort of where that is, we've got a wee little heat map somewhere. So a lot of the harsh braking happens in urban areas. That's where a lot of the other vehicles are, so it kind of makes sense. You know, harsh braking happens in rural areas where there's no other cars on the road as a consequence of perhaps distraction or incorrect speed choice. But in the urban areas, you get a lot of harsh braking because you're just following too close, or there's another intersection that's causing you to slam on those brakes. So what we did is we actually took all that harsh braking and we run a spatial clustering model into that and started coming up with these nice little clusters here. So this is a DD scan density based clustering, and we wanted to try and find these really dense locations and just sort of strip out all of the noise. And more importantly, we wanted to find where the crashes were in the network and do the same thing for those. I'll zoom out and find some. There you go. So we've got, we did the same thing for the crashes that happen in the network. And where it becomes interesting is looking to see where we've had crashes in the red, and we've had harsh braking clusters, and they spatially overlap. So there's a relationship there somewhere, if not just a spatial relationship. But what if we could have a look at the attributes from that harsh braking cluster, look at all of that 1.4 million times more data than we have for crashes, to see whether there's some characteristics we can use to predict where there should be a crash based on a known harsh braking data. And that's kind of what we did. So we took every single cluster of harsh braking data that we found, and we drew a nice little concave hull around it. We married it up with a crash cluster where we did the same, and then we had a look at the relationships between the two. So we found that out of just over 8,000 harsh braking clusters, 24% of them had a corresponding crash cluster, which is actually quite significant. But it also means that 76% of our harsh braking clusters don't have a crash cluster, and potentially some of them should, given the attributes that they share with the crash clusters. Of the crash clusters out there, just over half of them shared a harsh braking cluster. So we saw this really strong relationship between crashes and harsh braking here. But we wanted to do something a little bit different and have a look at the not just the spatial overlap, but the temporal overlap as well. So we took what you would normally do with the Hausdorff distance, where you measure the similarity between those two concave hulls, but we added a third dimension being time. And we were really interested to see whether there were clusters that had a lot of harsh braking, then had a lot of crashes, as opposed to the other way around. I mean, we're still interested in those other clusters because that spatial relationship is still very important to us. This didn't work out as well as we'd hoped. There were some clusters that did show that strong correlation. This is just a visualization of that. But we thought it was kind of a cool thing to do, and it was a new technique that we hadn't tried before. So some of the other considerations that we took into account were the turning choices. So a vehicle travels along the road, has a harsh braking event because of reasons. Then what happens? Where did he or she go after that? Did they turn left? Did they turn right? Did they go straight? So most of the time they went straight. And I think this was indicative more in the urban areas where, you know, external factors were causing the vehicles to harsh brake. And I don't want you to think that harsh braking is a bad thing. I'd rather a truck that's travelling down the road brake if my child walks out in the road. Harsh braking isn't necessarily bad. But there was also this asymmetry between left-hand turns and right-hand turns after harsh braking, which is really interesting. And in New Zealand, we drive on the left. So if you're turning right, you're crossing traffic, basically. So when we looked at some of these intersections, you know, we noticed that there was perhaps some indecision happening, or there wasn't enough notification of speed of the oncoming vehicles, or maybe the oncoming vehicles were travelling too fast and the driver couldn't judge that turn as well as they should. There's a little bit more work that we want to do in this area. And then some other areas that we fed into the model, whether it was a rural or an urban area, what the speed limit was, the type of vehicle, how old was the vehicle, what the start speed was and what the end speed was. You know, and this was, you saw this in the map where a lot of this harsh braking happens in these urban areas. So our urban speed limit is pretty much 50 kilometres an hour. It's not going to work now, is it? There you go. So in the urban areas, we see a lot of harsh braking. So that kind of overshadowed the model quite a bit in terms of the start speed and the end speed. But we got these really massive harsh braking drops going from 100 kilometres an hour down to 0. And those are sort of serious. You know, why did they do that? And then you get little ones where they're just sort of tapping on the brakes, and perhaps they're stuck in traffic, and they're just at the lower end of the scale. So at the end of this is what we found. So we were interested in where are the harsh braking clusters that had no crashes. So this is one example. This cluster shares a lot of the attributes with the other harsh braking clusters which did have crashes. So these are the false positives that we found. There's 101 of these around the country, which is a lot to deal with. But what we want to do now is go through these 101 and bring in a lot of other attributes that we didn't consider for this model around the geometry of the road, and then work with our partners, who incidentally are our customers because EROAD is so big in New Zealand, to put in place interventions. And that could be something really, really small, like a sign, or it could be some better road markings, or it could be removing some line of sight issues. And that's the real point behind this. So when we started talking to our customers that actually engineer the roads, they came up with a lot of these small interventions that could be put in place, and we could learn much, much faster than the existing traditional methods where we're spending hundreds of thousands, if not millions of dollars, putting into place interventions, waiting 3 or 4 years to see if they've worked. And we came up with this kind of this overview where that safe systems approach kind of replaces that question mark that you saw before. And instead of starting with a crash, we can actually focus more on the left-hand side. We can measure this driver behaviour. We can put in place some really small, cost-effective interventions, and then we can very quickly measure the efficacy of those within days or even weeks. And we don't have to sit on the right-hand side. We don't have to suffer the death and serious injury and all the bad stuff. We can start seeing where the tip of the iceberg is. And that's kind of our goal with this research. So I'd love to answer any questions you have. Thank you. That's really Reza.
Does this mean that you have data from every single truck and vehicle driving this? Or what's the sample data?
So we're sitting at about 40, just over 40% of all heavy vehicles, but a big proportion of our data set is light vehicles as well. So it's a smaller proportion of New Zealand's light vehicle population because that's much bigger. But yeah, it's definitely a significant data set for the heavy vehicles. So a lot of what we do is around understanding the road maintenance and the effect of heavy vehicles on the road. But that light vehicle fleet offers opportunities in urban areas that the heavy vehicles don't generally go into.
What's the definition of a harsh braking event?
So we have a bunch of accelerometers on board at our device. So we have some thresholds that they change from time to time. But we filter out the light harsh braking events. So we measure the G-force basically, and I think anything under 0.35 G we don't really consider as a harsh braking event. So if it's just sort of tapping on the brakes, the 0.1, 0.2.
So how do you know the guy just didn't hit a bump or something?
Well, we know the direction of the G-force. So from the accelerator, we know which direction the acceleration was in.
So you're not looking at change of speed from the engine bus?
That's part of it as well. Yeah. There's a bunch of inputs. So that box that we built, there's a whole bunch of inputs that come into that.
Are there other metrics of driver behavior you can collect? Like one thing I'm thinking of is like centripetal force, like around a curve.
Yeah, absolutely. So another piece of work that it was too much to talk about today is we're looking at the trajectory of vehicles around corners and looking to see where the out of context curves are. So corners are designed for a specific purpose and they sort of stay there for a number of years, right? But then that purpose changes depending on what the upstream demand is of that corner. So we've had situations where people have come to us, the councils have come to us and say, well, now we're seeing a whole bunch of forestry vehicles coming down this corner. The corner's not designed for that, and the forestry vehicles are going on the other side of the road, hitting the apex and then going on the other side of the road again because they're so big. So that's cool. They've identified that and they've come to us with help. How do you do that across the entire network? That's where it's more interesting because there's other corners where that's not being identified.
So cultural question, so you've got these boxes on heavy vehicles. So clearly that's something that the government has said this is going to happen. And you've got a huge amount of data. Mm-hmm. What would it take to get them into all vehicles, into light vehicles? So
the government hasn't demanded that an electronic solution come in. So in New Zealand, the road user charge system, go back to it. So RUC on the left-hand side, the labelling system, that's mandated. Across heavy vehicles, in fact any diesel vehicles, any vehicle that uses diesel, because they pay less in a fuel tax. Petrol vehicles pay an additional fuel tax, but it's an optional electronic solution. Mm-hmm. So in New Zealand, I think it's about 54% of all road user charges are electronic, and we're about 80-something% of that. So we've got the lion's share of all the electronic work. I don't know the answer to the next question. There's a whole bunch of issues around, you know, privacy, cost, all that sort of stuff when it comes to mandating this. I know that, you know, around the world there's challenges around how do we pay for our roads, right? And there's a lot of trials in the US on what do we do? You know, we can't just keep bumping up the fuel tax. You know, something might have to be looked at. So, you know, up in Oregon, we're up in Oregon, they've got weight mileage tax, you know, and so we produced a solution which is very similar to this, but it's a post-pay system instead of a pre-pay system. But the same device runs around the United States. So we've got, I don't know, 25, maybe 30,000 of these devices around the US at the moment as well.
I love the data that you got.
Yeah, it's fantastic.
Amazing.
Yeah, but I think the key thing is, you know, our core business is up on the right-hand side there. It's helping our customers be better. And you know, what we do with the data really does come back to this sort of mission of EROAD. Like, we want all of the communities to be much safer and have better roads.
Are you able to look at individual characteristics of the drivers, like their age, their gender, how long they've had a license, or is that?
No, New Zealand's got some pretty strict privacy laws around that sort of stuff. I think it would be interesting, but I think when we interact with the driver, we do it in real time with products on the actual device itself. So, you know, we alert them when they're speeding or when they're about to speed, and we say, hey, you got to slow down now, you know. So doing a sort of a model trying to find those demographics is almost at ambulance at the bottom of the cliff level when we can actually talk directly to the driver. So we do run other products, like we run a leaderboard where we know the best driver in the whole country and the worst driver in the whole country, and we run competitions, and it's amazing, like truck operators will do things like, you know, here's a morning tea for the best improved driver for the week, which is awesome, and you see the scores improve, and you know, these guys feel really proud that they can actually drive safely on the road now, and you know, they're always one-upping each other, right?
Oh, cool.
Yeah. Anyone else? Nope.
Have you looked at weather impacts?
Yeah, we do. So we've got quite a good network of weather stations in New Zealand. We looked at weather and speed one time, and obviously there's a strong correlation when it's, you know, nice and sunny out, people tend to drive much faster. One thing that we're really interested in is sunstrike. So New Zealand sits really low on the planet, and we have really bad sunstrike issues. There was a researcher out of Hong Kong that built this really nice topographical model of, you know, what's the sunstrike likelihood at that particular time of day, given the road inclination, which is awesome, and I'd love to try and highlight that in the country.
What is sunstrike?
Oh, the sun's glaring in your eyes. Yeah, it's quite challenging driving in New Zealand. Yes. Well, come up and ask me any questions later if you have any that you didn't think of. Thank you.